This is John Black, Super Chemist. This is part 2. How to make benzyl chloride. Now, if you're going to buy a special UV light that just does UV, keep in mind, just getting 300 to 400 nanometer, that doesn't mean it's going to work because of a thing called intensity. And I didn't look this up. I don't know if that's the correct word or terminology. But by intensity, I mean if you have 1 photon per second, you know, because it's a type of UV light that's attached to your key ring, and it's tiny as heck, you know, it runs on a little tiny battery or whatever. That may not be good enough, you know, it may not be good enough to do the reaction fast enough. You might be there for days and days and days just trying because you don't have enough intensity. You know, you don't have it bright enough. You have the right wavelengths, but you just don't have enough of those wavelengths to do a fast, quick job. You know what I'm saying? So keep that in mind if you buy a UV light. I was curious, and I was just going to put this formula down and tell you if you want to figure out, you know, what you need exactly. Here's the formula, and I got carried away and I did it myself. So here's the formula. Alright, now this is like my 3rd attempt at this video with this math, okay? My whole problem, and I'm going to put a link to the site where I got, because I got 400 nanometers. I looked online on a chart, and it said 10 to the 15th, and you can see right here, it is not 10 to the 15th hertz, it is 7.5 times 10 to the 14th hertz. That made a big difference. I'm going to put a link to that site so you can see for yourself how they messed it up. You look at the chart where it says UV light 400 nanometers, and it has the wrong thing. But what's funny is the same chart has visible light of 400 nanometers, and it puts the correct hertz. Out of the millions of charts, I had to pick the one that had the typo. Anyways, this is how you do this, all right? We want to break chlorine-chlorine bonds. So we want to know how much energy we need to break those bonds, right? We're going to first find out 400 nanometers is the weakest UV. Let's start from there. Let's say we want to use 400 nanometers of light, okay? We use this equation, E equals HF. H is just the a constant, Planck's constant. That's right here. It's in joules seconds. And then you multiply it by V, which is frequency, and that's in hertz, or seconds per wave, or seconds per photon. I prefer seconds per wave in this one. So you just multiply these to get your E. H times V equals E. So I take my H, I take my V, right, that I got off the chart, I multiply them, and I get this. That's how many, because the seconds cancel out, and you're left with joules per wave or joules per photon. So every photon is going to give me this much joules. And I changed it over to this number here because I want everything to be 10 to the minus 19th power so that I can compare just this and not worry about this. So you can see this is how many joules each photon of 400 nanometer light will produce. Now, is that enough for a chlorine-chlorine bond? I looked online, I got this number here, and that tells you how much, they're called bond dissociation energy charts, and I looked up a benzyl. You can't just look, or no, I looked up chlorine-chlorine, a chlorine-chlorine bond, and this is what it said. Now, I just want to know how much it is for one bond, not a mole, right? So how many bonds are in a mole? You know what that Avogadro's constant is, 6.021, or in this case I put 6.022 times 10 to the 23rd. The moles cancel out and you get joules per bond. How much energy, joules, does it take to break a chlorine-chlorine bond? This is the answer right here. And you can see that this is lower than this. This is 4.9 from a photon, and you only need 4.0 to break the bond. So obviously it can break a chlorine-chlorine bond. So 400 nanometers is great so far. right? I wanted to see exactly what nanometers corresponds to this energy, right? This energy is 400 nanometers. How much energy is this? What wavelength produces this exact amount of energy? And again, we use this same formula. We just rearrange it so that it gives us the V, which is the frequency, right? All right, so I take my energy right here. That's how much it takes to break the chlorine-chlorine bond. Divide it by Planck's constant, and I get frequency in hertz. Now, I just looked at like a moron. I looked at charts on the internet, and this is what I got as the corresponding wavelength, 557.6 nanometers. I later found out that that is incorrect, and that is when I decided to tell everyone, do not use these charts. All of these wavelength energy charts or wavelength frequency charts, they're all wrong. Half of them are all missed. Just don't even use them, okay? And what I should have done from the first place is just use math. Math will never fail you, okay? Whereas charts, they can, all right? I've never seen charts that were so messed up like this on so many different sites that it's unreal, okay? So let's figure this out, right? Now, here's our equation that we know, E equals HF, or HV. Now, V, okay, which is the frequency, is time per wavelength, right? And I mean speed per wavelength. And our speed is always the same. It's the speed of light, because it's EM waves, right? So that's a constant. It's the speed of light. So if I want to know the frequency, I would use this formula right here. I would take the speed of light and I would divide it by my wavelength. And that's what I do down here. See, the speed of light is 3 times 10 to the 8th meters per second. And now, since we're using meters, we have to change this nanometers into, what do you call it? We have to turn them into meters, right? Now, up above, we already said that we got from charts, it was 7.5 times 10 to the 14th hertz, or seconds per wave, right? We're doing this math to figure it out to make sure that it's right. And the way you do that is you take your nanometers and you just replace the nm with 10 to the 19th power. It's that simple to change it over, to convert it. It's that simple. If you had 300 nanometers, it'd be 300 times 10 to the negative 9th. If you had 200 nanometers, it'd be 200 times 10 to the 9th. It's that simple. Erase the nm and put in a 10 to the negative 9th power and an m per wave. That's it. That's how you convert it. So I did this math and I came out with 7.4 times 10 to the 14th seconds per wave, because the meters cancel out, and seconds per wave equals hertz. So that is correct, okay? If I would have done this math in the first place, I would have realized that 10 to the 15th was wrong. But I trusted the chart like an idiot, okay? Like I said, I'm putting a description, I'm putting a link to that site so you know not to ever use that site. Okay, now, so we did that. Let's check this now, right? Remember this? This is the how much nanometers you would need to break a chlorine-chlorine bond, right? And we said this was the hertz, and then I got on the chart to be this, 557 nanometers. Well, let's do the math and see if that chart is a big freaking liar. Okay? So again, I take my speed of light. I have, remember up here, we know the hertz is correct because we did it mathematically, right? We know this hertz is correct. We did it mathematically. What we got off the chart was the nanometers, right? So I take my speed of light, I divide it by the hertz, or the frequency, second per wave that I had, right? Because I want to get my nanometers. I want to get my lambda. Lambda equals C over V. And there's C over V. So anyways, I plug it into the calculator, I get this. I want to transform it into 10 to the negative ninth, right? Because that will be, I can just erase it and put nanometers, right? But if I make this number smaller, I have to make this number bigger. I did it by 2, right? 7 and 9, that's a difference of 2. So I move my decimal over 2. I got 494 times 10 to the ninth meters per wave. I want nanometers. So I just scribble off the 10 to the minus 9 and I put nanometers. It's that simple. Now, is 494.61 the same as 557.6? No, it is not. It is not even close, really. So this chart is a lying piece of garbage, just like the other chart was a lying piece of garbage. So keep in mind, these wavelength frequency charts, they're all garbage people that put garbage misinformation up. Okay? Do the math. The math makes it easy. So what does this tell me? This tells me I need 494.61 nanometers of light to break a chlorine-chlorine bond. Anything longer, because the longer the wavelength, the weaker it is. The shorter the wavelength, the stronger it is. So that means if I have any wavelength that is longer than this, say 495 nanometers, it will not have enough energy, right, to break the bond, because the longer the wavelength, the less energy. And so I would need something that had either this exact wavelength or a shorter wavelength, right? And 400 nanometers is lower than this number. So 400 nanometers UV light is obviously going to work to break your chlorine-chlorine bonds. Now the thing about this is you're going to make some carbon-chlorine bonds. And even if it's an alkyl group and you have a C-Cl bond, if you have the benzyl group and this has an H instead of a C, those are all harder to break than this benzyl carbon-chlorine bond. Okay, this is the easiest bond when you're doing halogenation. This type of bond is the easiest bond. It's easier than, say, you have DCM, dichloromethane. Getting a chlorine group off of an alkyl group is hard compared to this. Okay, so your light can break this. I mean, if your light cannot break this, it ain't going to be able to break any of the other ones, right? Because this is the weakest one. If you can't break this, you can't break the strong ones, right? So let's figure out how much energy is needed to break a benzyl carbon chlorine bond. That's the bond you're trying to make, okay? Because you don't want to break that, right? You're making it. So let's see how much energy it takes to break it. Again, we take the joules per mole we get off of a chart, a bond dissociation energy chart online, right? They all seem to be pretty good. They're not like the wavelength frequency charts that suck, okay? Then you divide that because I want to cancel out the moles and get how much joules it is per bond. This is joules per mole. I just want to know one bond of the mole. So I divide it by what a mole is, or how many bonds are in a mole, and I get this number here. 4.725 times 10 to the negative joules per bond. That means I need, if I have a photon that has this much energy or more, it will break that benzyl carbon chlorine bond, right? Now, what was 400 nanometers? How much energy was it? It was 4.96. Now, 4.96, obviously they're all times 10 to the negative 19. 4.96 is bigger than this, only slightly. You know what I mean? 4.96, 4.725, they're almost the same number, but it is higher, okay? So 400 nanometers or UV light is not, it will work, you know what I mean? It's going to break the chlorine bonds, that's for sure. It's going to barely, if it can barely break this one, it won't break any other bonds, right? But it can break this bond. So that's a no-no, okay? So let's see what wavelength corresponds exactly to this much energy, okay?